Okay. Yes. So what I was discussing, wait. Yes. So this is a signal generator part. Okay. So here the integrated output that is given to the voltage comparator multi-vibrator, and their output is then given in the amplifier as a square wave, as a triangular wave, and as a sine wave. Now next we are moving to the wave analyzer part. Let us do that. Okay, so from this wave analyzer, we can have a spectrum analyzer. Now, in this introduction of this wave analyzer, you can see it's very well known that any periodic waveform can be represented as the sum of the DC component and the series of the sinusoidal harmonics. Okay, so analysis of any waveform that mainly consists of determination of the values of the amplitude, frequency, and sometimes the phase angle of the harmonic component. Okay, now graphical and mathematical methods that may be used for this purpose that we will use, but these methods are quite laborious, means it needs some time, it needs much effort. So analysis of a complex waveform here can be done by electrical means using a band pass filter network to to single out the various harmonic components. Now, the network of this type pass a narrow band of frequency and provide a high degree of attenuation. Now, what is a wave analyzer? Wave analyzer, in fact, is an instrument that is designed to measure. Okay, so this is a what? An instrument, simple. An instrument, okay, designed to measure, designed to measure relative amplitudes of single frequency components in a complex waveform. So simple thing, wave analyzer, what is that? It is an instrument that is designed to measure relative amplitudes of single frequency component in a complex waveform. Basically, the instrument here acts as a frequency selective voltmeter, which is tuned to the frequency of one signal while rejecting others. So what they actually do, here the instrument act as a mainly frequency selective voltmeter that accept one signal, reject other signal, that type. The desired frequency selected by a frequency calibrated dial, okay, to the point of the maximum amplitude. Now the amplitude then again indicate either by a suitable voltmeter or a CRO. Clear? Now, one more thing, let me tell you, I'm just elaborating this diagram. So I'm elaborating the diagram. I think it's visible to you. Now, first in this figure, you can find resonant wave analyzer. So what I told, what is a wave analyzer? What is a wave analyzer? It is an instrument that is designed to measure relative amplitudes of single frequency components in a complex waveform. So here in this particular picture, that is figure 22.21, you can see here written resonant wave analyzer. So what is this? A very simple circuit of a resonant wave analyzer. So this circuit actually uses a LC. You can see your LC resonant network. Where is the LC? This is the C, this is the L. Okay, LC resonant network, which can be tuned to a particular harmonic component that is to be measured. Okay, now the signal is rectified and measured by a PMMC instrument calibrated to read the peak value of the sinusoidal voltage. So the signal, whatever signal, I mean, see this circuit that is uses an LC resonant network, which can be tuned to a particular harmonic component to be measured. Now, the signal which is rectified and measured by a PMMC instrument, that is again calibrated here. See here, the PMMC instrument is connected, that is calibrated again to read the peak value of the sinusoidal voltage. Now, the LC resonance circuit that passes only one frequency. Okay, so LC resonance circuit that only passes only one frequency, while it highly attenuates the signal of the other frequency. So it only allows one frequency to pass while it attenuates the signal of other frequencies. Now, several such circuits may be used, each tuned to a different frequency with their outputs that is connected through a selector switch to the rectifier and indicating some device. So indicator device are always connected here. That may be a voltmeter or the CRO. Now this simple circuit suffers definitely some disadvantages. That is why we go for some advanced topics. So what are the disadvantages? One is ability of the circuit to differentiate or distinguish between the components of two frequency. Okay, because I told you many frequencies are there, but this particular resonant wave analyzer, they can differentiate or distinguish between the components of two frequencies. Its resolution, that is, we have to check what is the resolution. It's poor. Now, if fixed tuned LC circuit is used, then what will happen? The frequency of the component must be known. So if fixed tuned LC circuit is used, so what is used? That is used fixed tuned LC circuit. Okay, fixed tuned LC circuit is used, then what will happen? The frequency of the component must be known. Third point, at low frequency, very large values of L and C are required and their physical size rather becomes impracticable. Means, you know, at low frequency, means you have to see that at what frequency this resonant wave analyzer will work. So maybe at low frequency. So very large value of L and C are required and their physical size will become impracticable. Now in this particular picture, however, in this system is useful in some applications, is resonant wave analyzer. Okay, and the applications, they are particularly where, you know, fundamental frequency is known and where the qualitative rather the quantitative analysis is required. So you remember one thing, in this particular resonant wave analyzer, what you require? You mainly require, wait, okay, yeah. So in this particular resonant wave analyzer, mainly what you require qualitative, you require mainly quantitative analysis. Okay, quantitative analysis. Clear? So this is the fact. Now next come, that is heterodyne wave analyzer. So what is a heterodyne wave analyzer, or you can name it as wave meter. Okay, so this is the heterodyne wave analyzer or a wave meter. Important thing, this one. So what is a heterodyne wave analyzer or a wave meter? Now heterodyne wave analyzer has certain advantages and overcomes some of the difficulties that is being encountered in the resonant wave analyzer. Okay, so this you have to keep in your mind. Definitely resonant wave analyzer has some drawbacks. Okay, that is why and there are some difficulties in resonant wave analyzer. That is why we are shifting towards a heterodyne wave analyzer or a wave meter. Now, a heterodyne wave analyzer, it uses a highly selective fixed frequency filter. So you just check it out, this particular diagram of this heterodyne wave analyzer or a wave meter. Here you see input signal. This input attenuation is a mixer, and here you have oscillator. Here is a frequency range, frequency tuning. Then here it is, this is the bandwidth. Okay, here a fixed frequency active filter is there that I was talking about. That in the heterodyne wave analyzer, they use a highly selective fixed frequency filters. And here is the amplifier detector. Okay, and the last block is, let me tell you, last block, I think it is, let me see what, VTM or TVM, which I told you, na, TVM type, or it is called VTVM, whatever. Okay, this is the thing. Now, one thing you remember that this actually the output of the variable frequency oscillator. Now, what is the meaning of the word heterodyne? Let me tell you. This heterodyne, right? Heterodyne. Heterodyne means actually mixed. Okay. Heterodyne means actually mixed. That means what happened? The output of this variable frequency oscillator, okay, is heterodyne or mixed successively with each harmonic of the input signal. Okay, so remember one thing, what is happening? The output of a variable, just a second. Hello, Monica. My voice is audible. एक बार confirm करो, Monica.
Yes, ma'am.
Okay. Yeah. So I was discussing here. It is a TVM or VTM. So let me discuss with you what is the working of this heterodyne wave analyzer. Now the output of the variable frequency oscillator is heterodyne or mixed successively with each harmonic of the input signal. So in this system, the signal from the oscillator heterodyne with the input signal to produce output signal having the frequencies equal to the sum and difference of the oscillator frequency F0. So we have two frequency. One is oscillator frequency. Okay, one is oscillator frequency. Another is frequency F. Frequency F. This is the frequency F, and this frequency F of the input signal. Okay, input signal. That is, you will be having one is F0 plus F and another is F0 minus F. So thus a continuous coverage over a wide range of frequencies obtained here instead of discrete steps in the case of resonant frequency oscillator. Now, since each harmonic frequency is converted here into a constant frequency, here it is possible to use highly selective filters, which I told you this is fixed frequency. Okay, so what they are doing, they are converting the frequencies into a constant frequency and definitely active filter. So this active filter is somehow the quartz crystal type. Quartz crystal type. So this active filter is actually quartz crystal type, and thus this circuit ensures that the constant frequency signal corresponding to a particular harmonic being measured and is passed through the filter. Okay, and is metered by the metering circuit. Now the output meter employed is usually a balance bridge. So this is the balance bridge called VTM or TVM. Now in heterodyne wave analyzer, what actually happened? The meter reading is directly calibrated here in terms of voltage. Okay, so so basically here in heterodyne wave analyzer, what happened? The meter reading actually, what meter reading? The meter reading is directly calibrated in terms of voltage, and therefore they are sometimes known as frequency selective voltmeters. Okay, so heterodyne wave meter may be used as distortion meters. So heterodyne meters, they are also called as distortion meters. Clear? Now distortion meters, now when they compare the amplitude of the harmonics of the impressed voltage with the reference source. Now the frequency of the harmonic is read off directly on the calibrated dial. Normally the network which is employed here is a low pass filter in the input circuit which excludes the sum of the frequency and passes only the difference of the frequencies, that is F0 minus F. So as we are discussing about the so this heterodyne, we have till now what we have learned, we are learning about heterodyne wave analyzer. Okay, now slowly we will move to some distortion analyzers. Okay, so let me show you the picture. Okay, let me first discuss with the equation part. Is this PPT visible? Hello, Monica, is it visible?
No. Yes, ma'am. Whiteboard is visible.
Whiteboard. Okay. Harmonic distortion analyzer. Now, what happened here actually? Have a look here. Till now we were learning harmonic wave analyzer. Okay, so whatever we have discussed, that is heterodyne wave analyzer and resonance wave analyzer. Now we will discuss harmonic distortion analyzer. Introduction part, whatever is introduction is that this is another measurement device which provides information on the waveform of an alternating voltage or current. Okay, that is the harmonic distortion. So if you're asked what is a harmonic distortion analyzer, you can say another measurement device that provides information. So first is provides information on the waveform, provides information on the waveform of an alternating voltage or current. Okay. This is the harmonic distortion. For what harmonic distortion analyzers are used. And this type of measurement is used for testing of the amplifier. So where we use this kind of device, first is definitely testing of amplifiers, and networks to what extent distort the input signal. Definitely we need distort. It is a harmonic distortion analyzer, so we have to check whether the input signal is not distorted. So a measure of the distortion represented by a particular harmonic is simply the ratio of amplitude of harmonic to that of fundamental. So here what you need to know that a measure of distortion represented by a particular harmonic is simply the ratio of the amplitude of harmonic that are fundamental. So harmonic distortion can be represented by, if I say harmonic distortion, that is HD, can be represented as, that is D2 equals to E2 by E1. I'm telling you what is E2 and E1. Acha. Then D3 is equals to E3 by E1. Okay. And D4 is equals to E4 by E1. So where you can say Dn is equals to, where n is equals to 2, 3, 4. Okay. It represents the distortion of nth harmonic. It represents the distortion of nth harmonic. Okay. And En represents whatever you have En, that I was telling you. En means definitely many numbers we have used. So En is mainly here amplitude of nth harmonic. Okay. Clear? This is amplitude of nth harmonic. And E1 that you say, which is common in both, in all the distortion criteria, that is E1. E1 is the amplitude of the fundamental. Okay. So this is the thing. This is actually the harmonic distortion analyzers. Okay. So these are all the formulas which we have to keep in our mind. That is, harmonic distortion can be represented as D2, D3, D4, where D and N is this much numbers which represent the distortion of the nth harmonic, and En is amplitude of the nth harmonic, E1 is amplitude of fundamental, like that. Okay. So now I will move on to total harmonic distortion and distortion factors, all those. Wait. I'm sharing my whiteboard directly. Okay. So have a look on my whiteboard. The harmonic distortion or distortion factor is defined as what? What we know? D, we have to take a simple D where D is definitely the distortions, okay? And you have to take over the D2 square, okay, plus D3 square plus D4 square. This is the thing. And that will be equal to basically E1 and root over you take E2 square plus E3 square plus E4 square and then so on. So percentage harmonic distortion, if I say what will be that? Root over dot D2 square plus D3 square plus D4 square plus multiplied by 100, okay, like this, that is equal to E2 square plus E3 square plus E4 square plus, and this will be E1, okay, E1, this will be into 100. So this is my, one is my harmonic distortion or distortion factor. The definition is important. And the percentage harmonic distortion, this is also important. So harmonic distortion can be computed from the measurements of wave analyzer described earlier. So these instruments are available wherever distortion can be measured directly. So main thing, what is the function of this harmonic distortion analyzer? Mainly is to measure what? To measure distortion. Okay. And what is distortion? Distortion means what? Suppose a waveform, this is a very smooth waveform. This is called a smooth sine wave. Okay. But distorted sine wave will be like this. Okay. So this is actually a distorted wave. Now moving to the next slide. Next page. Okay. Now distortion meters, where we will discuss distortion meters. I'm writing here. What are distortion meters? Now this instrument actually operate on the principle of first measuring the, so first you need to measure the RMS value of the total wave, okay, of the total wave, and then removing the fundamental component by means of highly selective filter circuit and measuring the RMS value of harmonics only. So one thing you just keep in your mind that these instruments actually operate on the principle. Remember, this instrument actually operate on the principle of first measuring the RMS value of the total wave, okay, and then what? And then you need to remove the fundamental component by means of highly selective filter circuit and then measuring the RMS value of the harmonics. So the block diagram of a distortion meter that I will show you just now. First, the RMS value of total wave is measured with a selector that is switch position. So let me show you the picture once. Wait, just a second. Wait. Okay, I'm sharing a slide with you. Just have a look. This is the harmonic distortion meter. I think it is visible to you. This is the harmonic distortion meter. So what I was telling, in this particular figure, which is written harmonic distortion meter, what is written here? That first, the RMS value of the total wave is measured with selector switch. Here, selector switch, which one? This is one selector switch, that is one. And the circuit is adjusted that the meter reads 100%. The selector switch is then put to position 2. So there are two positions, position 1, position 2. Okay. And there's this cut in the filter which rejects actually the fundamental frequency component, and the meter reads the RMS value of the harmonic only. Now, thus the meter indicates the percentage distortion directly. Okay, percentage distortion directly. Now you come and see here in this particular figure that what are connected, there is a bridge filter. Okay, here is an amplifier. With the amplifier connection is PMMC meter and the rectifier. Clear? This thing, so this is the harmonic distortion meter. Then we will move to our T-bridge circuit. So a T-bridge circuit is commonly employed to reject the fundamental frequency. Okay, so this is a T-bridge filter circuit which is commonly employed to reject the fundamental frequency, and this circuit is shows like this. So it can be shown that if the circuit is tuned to the fundamental frequency, suppose you have F0 equal to 1 by 2 pi root over 2 by LC, okay, like this, and R is adjusted to satisfy the relationship, that is R is equal to QL, then XL by 4, like this. Then what will happen, where we can say this QL XL by RL, that is with you can say this RL as a where where I am saying that this QL is equal to XL by RL. Okay, so this RL is the resistance of the inductor. The attenuation of the fundamental frequency component is infinite under these conditions. Okay, so I think this is a T bridge. You can understand why T filter bridge, because input and output are here, and here two capacitors are connected. With that, inductor L is connected, and with the two capacitors in between, a resistance is connected. Okay, so two capacitors here are parallel to each other in series with a resistance. So it is actually a T-like structure. See, it is a T-shaped structure. I hope this is clear. Now, next we can move to, so this is the distortion meters and bridge T filter circuit. Okay, so next I will move to the spectrum analyzer. Let me start about spectrum analyzer. So I'm sharing my whiteboard again. Next is spectrum analyzer. What is spectrum analyzer? Now, spectrum analysis is mainly defined as the study of energy distribution across the frequency spectrum of a given electrical signal. Okay, so that is a spectrum analysis. Spectrum analyzer comes from actually the word analysis. Analysis. Okay, so analysis mainly defined as the what? Study of energy distribution across the frequency spectrum of a given electrical signal. So spectrum analysis, what is that? It is mainly defined as the study of energy distribution across the frequency spectrum of a given electrical signal. Now, the study gives valuable information about what? About first is bandwidth. Okay, bandwidth. Then you can say effects of different types of modulation and spurious signal generation. What is that? Spurious. Okay, so bandwidth, then spurious signal generation. The knowledge of the above quantities and the phenomena here are very useful in design of the testing of the radio frequency, RF, and the pulse circuitry. Okay, what is that? Radio frequency Now, so the spectrum analysis is divided again into two major parts or two major categories, okay, on account of the instrumentation limitations and capability. So what are they? This spectrum analysis are divided in two parts. That is, one is audio frequency, okay, and the second is radio frequency. One is audio frequency, second is radio frequency. One is audio frequency analysis, and second is radio frequency spectrum analysis. Okay, so this the RF spectrum analysis mainly covers a frequency range. This is the RF one. Okay, RF, and this